Gravity is one of the first things you learn about in physics class, and you learn, among other things, gravitational potential energy. The change in an object's gravitational potential energy when you're on the surface of the Earth is equal to the mass of that object times this constant, little g here, which we all learn is 9.8 meters per second squared, and then you look at the change in height. So if you took as an example, comparing the gravitational potential energy of a monkey who is 2 meters off the ground versus 4 meters off the ground, that change in height from the ground would double, so the monkey's gravitational potential energy would double. But what if the monkey just kept going up? What if that monkey found a space ladder and it could climb all the way into outer space? How far can we take this logic? It doesn't really make sense that his energy is going to be infinite if he just keeps climbing up and up and up, especially as he's getting farther away from the Earth. And we all know that gravity is very weak once you get into outer space, and eventually you can escape from the gravity of the Earth. So clearly we need to find a more sophisticated way of dealing with this idea of gravity, right? Yeah, astronauts just floating around in outer space there, not really feeling a strong pull back to the surface of the Earth. So we have to dig in a little bit deeper to get a more sophisticated look at gravity. It is something we can represent with a field diagram, meaning a bunch of lines with arrows indicating the direction of the pull of a force. So if you're standing on the surface of the Earth, the gravitational field would look something like this, a bunch of lines going into the surface of the Earth, and we would draw the arrows pointing down because that's the direction that you move when you're inside of that field. And when you have a diagram like this, you can look at how close together the lines are, how dense the lines are, to get an idea of the strength of the field and the strength of the force you would feel. On the surface of the Earth, essentially what you have are a bunch of parallel lines, because gravity is the same no matter where you go on the surface of the Earth, basically. But if you zoom out, the gravitational field looks like this. It's quite symmetrical, but it's sort of circular, following the radius of a circle. So as you get farther and farther away from the center, that's representing the fact that the gravitational field is weaker and weaker, meaning the force that you feel is weaker and weaker. So you can see how much farther apart the field lines are up here versus right at the center of the Earth. Gravity does get weaker, but how do we deal with that mathematically? Essentially, what that means is the little g that we learn as being gravitational acceleration, that's only an approximation that works when you're at the center, close to the surface of the Earth. So we're going to learn where that little letter g comes from. There's a more general equation called the Law of Universal Gravitation, this guy right down here. So that you can say more generally, gravitational force is not just m times little g, it's actually equal to the mass of both objects. You have to have two objects in order to have a gravitational force. Usually those two objects are whatever object you're doing calculations with, and the Earth is your second object. And you also need to know how far apart those objects are. When we're talking about objects on the surface of the Earth, we use the radius of the Earth in order to plug numbers into this equation. So if you plug in the mass of the Earth and the radius of the Earth and the value for this big G here, which is a universal constant, you can see it down there in the bottom left corner of the screen, and it's also in the IB Physics Data booklet. If you plug in all of those numbers, you'll find that it comes out to be small g. So on the surface of the Earth, if you plug in the approximate radius, which is about 6,400 kilometers, and the mass of the Earth, and the value of g, you will get very, very close to 9.8. So that's where that number comes from. But we can use other numbers and other masses to find the gravitational force between anything. And that is how we deal with more complicated, more big picture analysis of gravity, gravity in space, gravity between planets, gravity between the sun and the earth.